Why does cold water make you flinch? A question that seems simple. You felt it hundreds of times. Under the morning shower in a cold lake, or even just when washing your hands under cool running water. You touch it, your body reacts. You step away, and you think the story is over. Cold water, the feeling of cold. End of story. Right? Wrong. The moment the water touches your skin, a process has already begun. It's not just a sensation, it's a chain of biological reactions, and it doesn't stop when you step away. It continues for many minutes, for hours, sometimes for more than a day. But you don't see it, so you think it doesn't exist. That's the first mistake. You think cold is something that exists in the water, but it's not. Water doesn't contain cold. It only has a temperature. What you call cold is actually how your nervous system interprets a signal. On your skin are tiny receptors, thermoreceptors, and they don't measure temperature like a thermometer. They measure change, a sudden drop. That signal is sent as an electrical impulse, traveling along the spinal cord up to the brain. And your brain, which never touches the water, which never directly experiences the outside world, receives that signal and creates an experience. An organized illusion that you call cold. Think about that. You have never actually touched cold water. You are only decoding a signal. And in that process, your brain takes an incredibly complex physical system and compresses it into a single simple sensation. That is where your perception begins to separate from reality. And if you want to understand what is really happening, you have to stop asking what cold water makes you feel and start asking, what is it doing to your body? Now let's go deeper, because once you accept that cold is only a signal, the next question is no longer what you feel, but what your body does with that signal. When your skin is exposed to water around 10 to 15 degrees Celsius, something is triggered almost instantly faster than your thoughts, faster than you can even realize what's happening, and that is the sympathetic nervous system. This is the part of the autonomic nervous system responsible for the fight or flight response. And it doesn't ask for your permission before acting. This response has a very specific name in physiology, the cold shock response. It is not exaggeration. It is a measurable, repeatable, and well-studied phenomenon for decades, especially since the 1970s when scientists began researching what happens when humans fall into cold water. And what happens first is your heart rate speeds up. A normal person at rest has a heart rate of about 60 to 70 beats per minute. But with sudden exposure to cold water, that number can exceed 100 beats in just a few seconds. Not minutes, seconds. This has nothing to do with you feeling scared. It is a direct electrophysiological response to the thermal signal. At the same time, your respiratory system changes abruptly. You inhale quickly, forcefully, almost a gasp. This is known as the gasp reflex. In studies of underwater accidents, this is considered one of the most dangerous factors. Because if this reflex occurs while your head is underwater, you can inhale water into your lungs before you can react. What's remarkable is that you have no control over this reflex. You don't decide to gasp. It happens before you can even think. Simultaneously, the blood vessels at the surface of your body begin to constrict in a process called vasoconstriction. Blood is pulled away from the skin, from your hands and feet, and is prioritized to vital organs like the heart and brain. This is a survival strategy. Your body is saying, keep the important things alive first. You may not realize it, but your skin temperature drops faster than your core body temperature. And this vasoconstriction helps slow the loss of heat from inside. The important point here is that all these changes happen without any involvement of your conscious mind. You don't command your heart to beat faster. You don't ask your blood vessels to constrict. You don't decide to change your breathing pattern. Your system does it for you because it is programmed to treat a rapid temperature change as a threat. And here's the interesting part. Your body doesn't understand context. It doesn't know you're standing in a modern bathroom with clean, safe water. It doesn't know you voluntarily stepped into cold water. It only receives one single signal, rapid temperature drop. And from the nervous system's perspective, that signal means danger. Research by Dr. Michael Tipton at the University of Portsmouth has shown that this response is strongest during the first exposure and gradually decreases as you repeat the experience. People who regularly expose themselves to cold water have less intense heart rate and respiratory responses compared to beginners. This shows that the system can adapt. It can learn. Cold exposure, therefore, is not just a random experience, but a form of stimulus that can be trained, just like training your muscles or cardiovascular system. But to understand this correctly, you have to accept something a little uncomfortable. Your body does not distinguish between a voluntary action and a dangerous situation. You can tell yourself, I'm just taking a shower, but your system doesn't listen. It doesn't process language. It processes signals. And the signal it receives is sudden temperature change. This is why you feel shocked, even when you know you're safe. Your conscious mind and your body do not operate on the same logic. One is based on perception, the other on reflexes. And it is this mismatch that creates the experience you call cold. If you want to see this more clearly, think about the first time you step into cold water on a winter day. Before you can even tell yourself everything is fine, your shoulders have already tensed, your jaw has clenched, and your chest has taken a sharp breath. The response happens before the explanation. That means biology always comes before the story you tell yourself. And that is the key point. You don't use willpower to create the cold shock response. You only witness it. But this is only the first step. The cold shock response is not the whole story. It is only the switch. It is the starting signal. And when that switch is flipped, a deeper chain of processes begins to unfold inside your body, processes involving hormones, metabolism, the immune system, and the nervous system, things you don't feel directly, but that determine how your body functions for many hours afterward. If you stop at the feeling of cold, you've missed the most important part of the story. And when that switch is flipped, the real story begins. Because the cold shock response doesn't just make you breathe heavily or make your heart beat faster. It triggers a chemical cascade that runs through your entire body. As soon as the sympathetic nervous system registers that the skin is losing heat too quickly, the adrenal glands begin releasing noradrenaline into the bloodstream. This is not a vague change, but a measurable increase that can be detected in lab tests. In studies of cold water immersion in humans, plasma noradrenaline levels rise dramatically. A classic study showed that immersion in 10 degrees Celsius water triggers a clear norepinephrine response. And a 2000 study by P. Sremik and colleagues recorded noradrenaline increases of up to about 530% under certain cold immersion conditions. Think about that. You step into cold water for a few minutes, and your body responds by pumping a large amount of a chemical designed to make you alert, vigilant, and ready to act into your blood. Noradrenaline doesn't exist to make you feel strong. It exists to prioritize survival. It increases alertness in the cerebral cortex, speeds up neural reflexes, sharpens your attention, and shifts your system into a ready state. This is why, after cold water, you often don't feel sluggish. You feel as if someone just turned the lights on inside your head. But what's even more interesting is that noradrenaline doesn't travel alone. Along with it, dopamine also rises significantly. And I want you to be careful here, because dopamine is often described in a silly way as if it were only the happiness chemical. It's not. Dopamine is involved in motivation, in directing behavior, in sustained focus, in the feeling that you have the energy to do something instead of just sitting there thinking about it. In the same Sharmic study, plasma dopamine increased by about 250% after cold water immersion. That's a very large number. And the most important point is that this increase does not disappear the moment you step out of the water. Modern aggregated data on cold exposure show that some neurological effects, especially the state of alertness, energy, and focus related to dopamine, can last for many hours after the cold exposure ends. That means a very short physical stimulus can create a significantly prolonged neurological state. It's not 5 minutes of stimulus in exchange for 5 minutes of alertness. No. You get a few dozen seconds or a few minutes of cold exposure, and in return you get many hours of your nervous system operating in a different mode. This is the point where the whole story begins to shift, because now we are no longer talking about the feeling of cold. We are talking about how a change on the surface of the skin has led to a measurable reconfiguration in the chemistry of your brain and body. And that is something most people never think about. They think cold water is just a mental challenge, a test of willpower, something to prove they are tougher than others. But your body doesn't care about your self-image. It doesn't care whether you are disciplined or not. It sees a thermal signal, then automatically adjusts its entire neurological and endocrine state. You are not creating motivation when you step into cold water. Your system is doing it for you, and it does it through biology, not slogans, not through inspiration, not through positive thinking, through hormones, through neurotransmitters, through a chain of responses that was written into your body long before you even knew what the word dopamine meant. This is also why cold exposure is different from caffeine. Caffeine doesn't create a new state so much as it blocks fatigue signals by antagonizing adenosine. Cold water is different. It doesn't mask fatigue. It mobilizes resources. It activates a response. It shifts your system into a higher operating mode. And therefore, what you feel afterward is not simply euphoria. It is a recalibrated neurological state. Your body is adjusting its own internal dial without you having to touch it. A very simple physical stimulus leads to a very complex chain of chemical reactions. A patch of skin meets cold water. Then the adrenal glands respond. Blood vessels respond. The nervous system responds. And your brain begins to operate in an entirely different chemical context. This is why I tell you that you cannot understand cold exposure if you only look at the subjective feeling. The feeling is only the tip of the iceberg. What really matters is happening underneath in the blood and the synapses, in the molecules you cannot see, but can measure. And when you start looking at it that way, you will see that your body does not react in isolated pieces. It reacts as a system. One signal comes in, and then multiple layers of adjustment are activated at the same time. There is no separate switch for the heart, a separate switch for dopamine, a separate switch for focus. They all linked together. And precisely because they are linked, the effect of cold does not stop at making you feel alert. It goes much further. It begins to touch the way you focus, the way you tolerate stress, the way you mobilize energy, and ultimately the way your entire physiological state is organized in the hours that follow. And when you begin to see that hormonal cascade, you will realize something even more important. It doesn't just affect your body, it directly changes your psychological state. Not in a vague way like, I feel better, but in a very specific sense that can be measured in neural activity. When noradrenaline rises, it increases brain alertness, boosts signals and attention networks, making you less distractible. When dopamine rises, it doesn't just create a pleasant feeling. It also adjusts the motivation system, making you more inclined to take action rather than procrastinate. These two systems together create a state you can recognize very clearly. A clearer mind, sharper focus, fewer wandering thoughts. And the important thing is that this state does not depend on you wanting it to happen. It happens because the chemistry in your brain has changed. A 2008 study at the University of Virginia observed that cold water exposure can reduce symptoms of mild depression in some subjects. This may sound surprising if you only think of cold as discomfort, but when you look at it from a biological perspective, it makes perfect sense. Depression, to some degree, involves reduced activity in neurotransmitter systems such as dopamine and noradrenaline. And when you naturally activate these systems through cold exposure, you are directly affecting the same mechanisms that many medications try to regulate. But here, there is no pill, no external chemical, only a physical stimulus and a biological system responding to it. This also leads to an interesting paradox. You create a form of acute stress to reduce chronic stress. When you step into cold water, your body reacts as if facing a threat. Heart rate increases, hormones rise, the nervous system activates. But because you control the duration and intensity of that experience, your system learns that it can enter a stress state and then return to normal without negative consequences. Over time, this changes how your body handles stress in general. Cortisol, the hormone associated with prolonged stress, tends to decrease at baseline levels when the body adapts to repeated cold stimuli. You are not removing stress from your life. You are training your system to handle it better. And this is completely different from the kind of stress most people experience every day. Stress from work, from information, from the constant stimuli of the modern environment is usually chronic, stress prolonged, without a clear end point. Your system is activated but never fully turned off. With cold exposure, it's the opposite. You activate strongly, then you stop. A clear cycle and cycle, and the clear end signal. And it is that clarity that allows your nervous system to re-establish balance. This is the point where many people misunderstand. They think the goal is to relax, to completely eliminate tension. But biology doesn't work that way. You are not designed to have zero stress. You are designed to handle stress efficiently. And what cold exposure does is not relax you in the traditional sense. It rebalances your system. It readjusts your level of response, your sensitivity, your recovery. It teaches your nervous system that it can go up then go down without getting stuck in an activated state. And when you understand that, you begin to see that the feeling of feeling better after cold exposure is not a vague psychological effect. It is the result of a system that has been recalibrated. You are not convincing yourself that you are better. Your body is actually operating in a different state. And that difference does not lie in your thoughts, but in the way your neurons are transmitting signals, the way your hormones are circulating in your blood, and the way your entire system is reorganizing itself after a very simple but very powerful stimulus. If you continue to go deeper into what is happening after your nervous system and hormones have been activated, you will begin to touch another layer of biology that is talked about less, but is extremely important: the way your body handles energy. More specifically, we are talking about a special type of tissue in your body called brown fat. Not the type of fat you usually think of when you hear the word fat. Not the kind that stores excess energy around your belly or thighs. Brown fat is an entirely different system. It is designed not to store energy but to burn it. In a major 2009 study conducted by Van Mark and Lichtenbelt and colleagues in the Netherlands, it was confirmed that adults actually have active brown adipose tissue, and its activity level increases dramatically when exposed to cold. Before that, many people thought that brown fat only existed in newborns. But this study completely changed the way we understand energy metabolism in adults. Brown fat operates through a mechanism called non-shivering thermogenesis, meaning heat production without shivering. When you are cold, your body has two ways to generate heat. One is shivering, where muscles contract to produce heat as a byproduct. The other is activating brown fat, where energy is converted directly into heat at the cellular level. And here is the interesting point. Inside brown fat cells, there are large numbers of mitochondria, the power plants of the cell. But these mitochondria operate in a different way than normal. Instead of using energy to produce ATP, the form of energy your body uses for its activities, they use a special protein called UCP1 to lead this process. Energy is not stored. It is released as heat. You are burning energy to produce heat without moving a single muscle. When you are exposed to cold, the sympathetic nervous system activates brown fat through noradrenaline, and these cells begin to burn energy at a high rate. That means your body is shifting into a mode in which energy is used immediately instead of being stored. And this is not a small effect. Studies show that people who regularly live in cold environments have significantly more active brown fat than people who live in warm environments. That means this system can adapt. It can be turned on or turned off depending on how you live. And this is where the modern environment starts to become a problem. You live in a world where temperature is controlled almost perfectly. You step out into hot weather. You go into an air-conditioned room. You feel cold. You turn on the heater. Your body rarely has to regulate its own temperature. And when a system is not used, it declines. Your brown fat does not disappear completely, but it becomes less active. It is like a muscle you never use. It is still there, but it grows weaker. Cold exposure in this context is not adding something new to your body. It reactivates a mechanism that already existed, a mechanism that your ancestors relied on to survive in cold environments. When you step into cold water, you are not only triggering the shock response or the hormone cascade, you are waking up a forgotten metabolic system. And that system does not only produce heat, it changes the way your body handles energy, the way you burn calories, and the way you maintain core temperature without needing support from the external environment. This leads to an important consequence. You are no longer completely dependent on the environment to regulate your state. Your body begins to regain some of the control it has lost in the modern environment. And when you look at this from a broader perspective, you will see that cold exposure is not just an uncomfortable experience or a mental challenge. It is a way to reactivate core biological systems that were once standard but have now become the exception. And when those systems are reactivated, the entire way your body operates begins to change, not immediately in a way you can feel, but clearly and measurably at the biological level. When you look at brown fat as an energy-burning system, the next step becomes very clear. Your entire metabolism begins to shift in a different direction. Cold exposure does not just activate one type of tissue. It forces your entire energy system to adapt to a new demand, which is to produce continuous heat to sustain life. And to do that, your body must increase its metabolic rate, meaning your basal metabolic rate. You are burning more energy, not because you are moving more, but because you are trying not to lose heat. This is a fundamental change because it happens even when you are standing still. In a cold environment, your body cannot save energy in the usual way. It must spend, it must burn fuel. A 2014 study published in the journal Cell Metabolism showed that exposure to cold not only increases energy expenditure, but also improves insulin sensitivity, a core factor in the way your body handles glucose. When insulin sensitivity increases, your cells become more efficient at absorbing glucose from the blood. This means that with the same amount of sugar, your body uses it better, stores less of it as fat, and maintains more stable energy levels. This is not a small effect. This is a change at the system level. It affects the way you eat, the way you store energy, and the way you use it throughout the day. At the same time, in a cold environment, fat oxidation, the process of burning fat for energy, also increases. When glucose is not enough, or when the system needs more energy, your body begins to mobilize stored fat and convert it into heat. But it is important to understand this correctly. Cold exposure is not a weight loss trick. It is not a quick way to burn calories to replace diet or exercise. What it does is change the way your system operates. It does not target a specific outcome like weight loss. It adjusts the entire metabolic mechanism. And when that mechanism changes, the results can appear as a consequence, not as the goal. One of the important concepts here is metabolic flexibility. The body's ability to switch flexibly between using glucose and fat as energy sources. In the modern environment, many people are stuck in a metabolically inflexible state, relying primarily on glucose and using fat less efficiently. This leads to fluctuating energy, feeling tired after eating, and difficulty maintaining a stable state. Cold exposure forces your body to become more flexible. It does not allow you to rely on only one energy source. It requires your system to switch continuously, to mobilize both glucose and fat according to demand. And over time, this ability improves. You become more efficient at using energy, not because you are trying, but because your system has been trained. This leads to a deeper change that many people do not realize. Your body shifts from an energy-saving state to an energy-consuming state. In a warm and abundant environment, the body tends to conserve energy, store it, and prepare for the future. But when you are exposed to cold, the message your system receives is completely different. It is not, hold on to it. It is, use it now. And when that message is repeated many times, your system begins to change the way it prioritizes. It becomes less storage-oriented, more flexible, and more efficient at handling energy. This is why you cannot understand cold exposure just by looking at the surface. It's not just the feeling of cold, not just hormones, not just hormone fat. It is a restructuring of the way your body operates at the most basic level, the way it takes in energy, the way it uses energy, and the way it decides when to store and when to burn. When your metabolic system begins to change, another system also begins to shift along with it, more quietly, harder to see, but no less important. The immune system. Most people never put cold water and immunity in the same sentence. They think immunity is about bacteria, viruses, medicine, vitamins, and sleep. They do not think about temperature. They do not think that letting your skin touch cold for a few minutes each day could change the way your body responds to inflammation. But that is exactly what makes this story interesting. The immune system is not a separate machine. It does not operate in its own isolated corner of the body. It is connected to the nervous system, to hormones, to metabolism, to the level of stress you experience every day. And once you understand that cold exposure is a form of controlled biological stress, you begin to see why it can affect immunity in a much deeper way than initial intuition suggests. A famous 2016 study at Radboud University in the Netherlands, conducted by the team of Matthijs Karks and Peter Pickers, drew a lot of attention because it showed something many people previously found hard to believe. Humans can modulate their innate immune response through physiological training, including cold exposure. In this study, participants were trained with breathing, focused meditation, and cold exposure, then injected with endotoxin, a component of bacteria used to create a controlled inflammatory response in the laboratory. The results were remarkable. The trained group produced higher levels of adrenaline, showed a stronger anti-inflammatory response, and exhibited fewer flu-like symptoms compared to the control group. That does not mean cold water turned them into superhumans. It means their immune system responded differently, and that is already significant enough. Because this is exactly the point where popular talk on the internet often ruins the whole issue. People say cold water boosts immunity, as if immunity were something where more is always better. That is too crude a way of thinking. A blindly stronger immune system is not always good. Allergies are an example of an overactive immune response. Autoimmune diseases are the same. What matters is not simply being stronger, but being more precise, more balanced, and more flexible. And cold exposure seems to achieve this not by pushing the immune system to a fixed higher level, but by adjusting the way it responds to stress and inflammation. Part of this story lies in cytokines, the signaling molecules that immune cells use to communicate with one another. Some cytokines promote inflammation, while others help calm it. When your body lives in chronic stress, poor sleep, overeating, lack of movement, or constant stimulation from the modern environment, the immune system can be pulled into a state of low-grade but prolonged inflammation. It is not the kind of inflammation you feel clearly, like fever or swelling. It is a smoldering, silent inflammation, but enough to change the way the body functions over time. And this is where cold exposure becomes biologically interesting. When repeated at reasonable doses, it creates a form of acute stress with a clear starting point and a clear ending point, and therefore allows the body to activate and then recover. This is completely different from chronic stress, the kind of stress without clear boundaries. You wake up with it, work with it, sleep with it. It does not come like a wave and then recede. It stays. And because it stays, the immune system never really returns to a balanced state. Acute stress can mobilize the immune system. Chronic stress wears it down. That is the core difference. Cold exposure belongs to the first type. It wakes the system up, but then it also allows the system to learn how to return to normal. It is this cycle that is truly important. Not the shock, but the shock followed by recovery. Not the activation, but the activation followed by rebalancing. Over time, this appears to reduce baseline signs of inflammation and adjust the cytokine response toward less chaos. You are not making the immune system bigger. You are making it less wasteful. You are making it react at the right time. You're making it less panicked. And that is very different. Think about it this way. A healthy immune system is not one that is always firing. A healthy immune system is one that knows when to respond strongly and when to stop. The problem with many modern bodies is not a complete lack of activation, but activation of the wrong kind, at the wrong time, and for too long. Cold exposure introduces a very clear signal. It tells the system, this is real stress. Start right now. End in a few minutes. And precisely because that signal is clear, your body can organize its response better. It mobilizes resources, then retrieves them. It creates inflammation when needed, then lowers it. It increases alertness, then recovers. This is something that modern psychological stress rarely allows. Emails never have a clear end. News never has a clear end. Anxiety is the same. But cold water does. You step in. The system responds. You step out. The system learns to return. And each time this is repeated, you are teaching your body something it seems to have forgotten, how to endure a strong stimulus without losing control. This is why I tell you that cold exposure is not just about willpower or discipline. It is biology. It is a signal with a clear shape, clear intensity, and clear duration. And your immune system, like every other system in your body, responds to that clarity. Not by becoming more aggressive, but by becoming more organized. And when you begin to look at it that way, you will see a pattern repeating from the beginning until now. A thermal signal enters the skin. The nervous system responds. Hormones rise. Metabolism changes. And then the immune system also shifts. No pot stands alone. No system operates by itself. Each layer of response is the foundation for the next. And the deeper you go, the clearer you see that cold water does not just make you feel cold. It is talking to your entire body at the same time. You may have misunderstood the nature of cold from the very beginning. You think that you step into cold water and perceive a property of the outside world. But if you look more closely, that is not correct. Cold is not something that exists in the water. It is not a substance, not an entity you can touch. Water only has temperature, a physical value measured by the energy of its molecules. What you call cold does not exist in the water. It is created inside you, and this changes the entire way you understand that experience. Your body does not respond to cold water as a concept. It responds to the temperature change at the surface of the skin. It responds to the rate of heat loss. It responds to data. The thermoreceptors on your skin do not know whether you are in a lake, in a shower, or in a laboratory. They have no language. They have no concepts. They only detect change and send electrical signals. These signals travel through the spinal cord up to the brain. And there, something very interesting happens. Your brain, which you think is you, never directly contacts the outside world. It does not touch the water. It does not sense temperature. It does not know what cold is in the physical sense. All it receives are electrical impulses. And from those electrical impulses, it builds a model, an interpretation, an experience that you call a sensation. This is a point that neuroscience has emphasized for decades. Perception is not reality. It is a map, not the territory. When you say, "I feel cold," what you are really saying is, "My brain is interpreting a set of signals in this way." And that means your entire experience is not a direct window to the world, but a simulation built inside your nervous system. Now let's return to cold exposure. If you look at it as an experience, you will focus on the sensation. You will think about the discomfort, about enduring, about overcoming. But if you look at it as an input to the system, everything changes. Cold water is not an uncomfortable experience. It is a physical signal entering your body, and that signal triggers a chain of biological responses that we have already gone through. The nervous system, hormones, metabolism, immunity. You do not need to like that signal. You do not need to interpret it in a positive way. Your system does not care. It only needs the signal. This is the point that most people miss. They try to change the sensation instead of understanding the signal. They think the goal is to get used to cold in an emotional sense. But the real goal, if there is one, is for your system to receive and process the signal more efficiently. When you step into cold water, you are not experiencing cold. You are feeding very strong data into your system. And that system responds according to rules that have been programmed in advance. This also explains why the same physical stimulus can lead to very different subjective experiences between individuals. One person may find it extremely uncomfortable. Another may find it almost neutral. But at the biological level, many responses remain the same. Heart rate increases. Hormones rise. Brown fat activates. Metabolism changes. Experiences differ. Biology is much more consistent. And this is where you can begin to separate the two things. What you feel and what your body does. You may not like the feeling of cold, but your body still carries out a chain of responses that are beneficial in many ways. You may like the feeling, but that does not change the biological mechanism behind it. Input is input. Output is output. Perception is only the surface layer. And when you look at everything that way, a new question arises, a question that few people ask. If your experience is only the way your brain interprets signals, then what are you really controlling? Are you controlling the sensation, or are you controlling the act of feeding signals into your system? Because if cold exposure is only an input, then you can start to see it as a tool, not a challenge, not a test, a tool, a way to provide your body with a type of data that the modern environment rarely provides. A clear, powerful, unambiguous signal. And when you provide that signal, your system responds. Not because you believe in it, not because you want it, but because that is how it is designed to function. This is the twist I want you to keep in mind as we continue. You are not interacting with cold as something external. You are interacting with the way your body processes information. And therefore, cold is not something you feel, but something your body processes. Your body is not built like independent blocks, like a machine that can be taken apart piece by piece. It is more like a network. And at the center of that network are two major systems that always work together: the nervous system and the endocrine system. The nervous system transmits signals quickly, almost instantly, through electrical impulses. The endocrine system is slower but more widespread, through hormones traveling in the blood. These two systems are not separate. They constantly talk to each other. A neural signal can trigger hormones. A hormone can loop back and influence the brain. It is a loop, not a straight line. And the important thing is this: when you introduce a signal into this system, you never activate just one part. Let's go back to the example you have already seen. A small temperature change at the surface of the skin. It sounds simple, but that signal is detected by thermoreceptors, converted into electrical impulses, sent up the spinal cord, up to the brain, specifically to the hypothalamus region. And from there, the sympathetic nervous system is activated. But it does not stop there. This neural signal activates the adrenal glands, releasing noradrenaline and adrenaline. These hormones enter the bloodstream and spread throughout the body. Your heart responds. Blood vessels respond. Brown fat responds. Metabolism changes. The immune system adjusts. Are you beginning to see what is happening? A thermal signal on the skin leads to a chain of responses that spreads across many different systems. This is exactly what is called the cascade effect in systems physiology. A small input signal is amplified through multiple layers, creating a large response at the output. You do not need a large stimulus to create a large change. You need a stimulus in the right place within a tightly connected system. This is not a new idea. In the field of systems biology, it has been shown that the body operates as a complex network where the nervous, endocrine, immune, and metabolic systems continuously interact with one another. No system stands alone. No response is completely isolated. When you change one variable, you are touching the entire system. And this explains why cold exposure can produce so many effects from a single simple action. It does not target one thing. It enters at the intersection of multiple systems at once. It is like touching a central node in the network where all the wires converge. Let's look back at what we have covered. You started with a sensation, but that sensation is only the top layer. Below it is the neural signal. Below that are hormones. Below that are metabolic changes. And even deeper is the adjustment of the immune system. These are not separate parts activated one by one. They happen simultaneously, overlapping, influencing one another. And therefore you cannot say that you are only affecting the nervous system or affecting metabolism. You are affecting the entire system. This is the point where many modern approaches fall short. People try to break the body into separate parts: medicine for the brain, diet for metabolism, supplements for immunity. But the body does not operate in that fragmented way. It responds as a network, and when you introduce a primal physical signal like cold, you are talking to the entire network at the same time. This also leads to an important consequence. You cannot change one part without creating effects that spread to the others. You cannot activate hormones without affecting the nervous system. You cannot change metabolism without affecting immunity. Everything is connected. And that is why a simple input like cold exposure can create such broad changes. Not because cold water has special power, but because your body is a system designed to respond in a connected way. And when you look at it that way, you begin to see something very clearly. Cold exposure is not a localized experience. It is not something that only happens at the skin or in the sensation. It is a whole system input, a signal that enters and spreads throughout your biological network. And when you understand that, you will no longer see stepping into cold water as a simple action. You are activating a system. If you've accepted that the body is a network system, then the next thing you need to understand is how that system amplifies signals. Because the entire power of cold exposure does not lie in the cold water itself, but in the way your body processes and amplifies the initial thermal signal. Let's start at the very first point, the thermoreceptors on your skin. When skin temperature drops quickly, these receptors detect the change and convert it into an electrical signal. This signal is transmitted through sensory nerve fibers at speeds that can reach about 50 to 100 meters per second, meaning that in just a few milliseconds, the information is traveled from your skin to the spinal cord and up to the brain. And the central point that processes this signal is the hypothalamus, a small structure deep in the brain that acts as the thermostat for the entire body. The hypothalamus does not just notice that you are cold, it compares the current temperature with an internal set point, and if there is a deviation, it begins issuing adjustment commands. This is where the signal begins to be amplified. From the hypothalamus, neural signals are sent down to the sympathetic nervous system, triggering immediate responses such as increased heart rate, blood vessel constriction, and changes in breathing rate. But at the same time, the hypothalamus also activates the HPA axis, hypothalamic pituitary adrenal axis, leading to the pituitary gland and then the adrenal glands releasing hormones into the blood. This is the point where the signal shifts from electrical to chemical, and the difference here is very important. Neural signals happen extremely fast, in milliseconds, but hormones, once released, can persist and exert influence for many minutes, even hours. That is why you feel the cold shock almost immediately, but its effects such as alertness or metabolic changes last much longer. This is the principle of neuroendocrine signaling, the coordination between the nervous system and the endocrine system to create a response that is both fast and sustained. And when you look at the entire chain, you begin to see a very clear pattern. A small input signal is amplified through multiple layers. Thermoreceptors only detect a change of a few degrees Celsius, but that information, when it passes through the hypothalamus and the neuroendocrine system, becomes a whole body response. Hormones increase by 200 to 300%. Heart rate increases by dozens of beats per minute. Metabolism rises, and the immune system adjusts. This is the amplification effect, and it does not exist only in biology. You see it in many other systems. A small electrical signal can turn on an entire power grid. A small data packet can spread across the entire internet. A small change at the input, if it hits the right processing center, can create a very large output. Your body operates on a similar principle. Cold exposure is not powerful because cold water is special. It is powerful because it touches the exact system designed to amplify thermal signals. And when that system is activated, it does not respond in a linear way. It responds exponentially. A small change, many responses to each response triggers another. This is why you cannot evaluate cold exposure only by the intensity of the initial stimulus. You must look at how the system processes that stimulus. And when you understand this, you begin to see something very different. You are not enduring cold in the usual sense. You are not trying to overcome an uncomfortable sensation. You are activating a biological amplification system that already exists in your body. And once that system is turned on, what happens next no longer depends on your willpower. It depends on how your body is designed to respond. So why does this system exist in the first place? And the answer lies in something you can no longer see directly in your modern life. The environment in which humans evolve. For more than 99% of human history, there was no hot water, no air conditioning, no temperature control systems. Humans lived in nature, where temperature changed continuously from day to night, from season to season, and from place to place. In many regions, temperature could vary by 10 to 20 degrees Celsius within just 24 hours. Hot days, cold nights. Hot summers, cold winters. And your body, the system you carry with you, was shaped precisely in that context. Studies in anthropology and evolutionary physiology have shown that humans did not evolve in a stable environment, but in a continuously variable one, where the ability to adapt to temperature changes was a condition for survival. The mechanisms you have just seen, blood vessel constriction, activation of stress hormones, heat production from brown fat, are not side features. They are the result of hundreds of thousands of years of natural selection. An individual who could not retain heat when cold would not survive the winter. An individual who could not adjust metabolism when temperature changed would waste energy inefficiently. And over time, the systems that help the body respond quickly, strongly, and flexibly to temperature fluctuations were retained. Brown fat, for example, is especially developed in newborns to help them stay warm before they can shiver. But modern research shows that adults still retain this system, though its level of activity depends on the environment. Vasoconstriction, the process of constricting blood vessels, helps preserve heat for vital organs when it is cold. Stress hormones, like noradrenaline, are not only related to anxiety as we think of it today, but are part of the system that helps the body respond quickly to a changing environment. None of this is random. It was designed for a world where temperature is not stable. And here is the important point. Your system is optimized for variability, not for stability. But the modern environment you live in does the opposite. You wake up in a room with stable temperature. You go outside, get in the car, enter the office, all of it air conditioned within 20 to 24 degrees Celsius. Your body almost never has to regulate its own temperature. And when a system is not used, it does not disappear, but its activity decreases. This is not a flaw, it is adaptation. Your body is doing exactly what it was designed to do. Conserve energy by not maintaining unnecessary functions. But that leads to a consequence you may be starting to recognize. Mechanisms that were once very important are now rarely activated. Brown fat is less active. The vasoconstriction response is less sensitive. The hormone system is not trained the way it once was. And when you step into cold water, you are not doing something extreme. You are returning your body to a type of signal it was familiar with for most of its evolutionary history. Cold exposure, in this sense, is not a biohack, not a modern trick to optimize the body. It is a return to an original condition that your system was built to handle. And when you look at it that way, the whole story changes. You no longer ask, why should I endure cold? But begin to ask a different question. Why am I living in an environment where my body almost never has to face cold anymore? And that is where the real issue appears. The problem is not that cold is too harsh. The problem is that you have had too little exposure to cold. And when you ask that question seriously, you begin to see the modern environment in a very different way. Not as a perfect step forward, but as a system that has removed almost all the variability that your body once depended on. Look at a normal day in your life. You wake up in a room kept at about 22 degrees Celsius. You step into the bathroom, where hot water is ready at an almost constant temperature. You put on clothes designed to keep stable heat around your body. You go outside, get into an air-conditioned car, arrive at an air-conditioned office, and then return home the same way. Throughout the day, the temperature around you fluctuates within a very narrow range, usually from 20 to 24 degrees Celsius. This is not random. Studies on urban living environments, especially in building science and environmental ergonomics, have shown that most modern living and working spaces are designed to maintain what is called the thermal comfort zone, a temperature range where humans feel most comfortable, usually between 20 to 24 degrees Celsius with humidity around 40 to 60%. This is a significant engineering achievement, but from a biological perspective, it creates something very specific, an almost unchanging environment. Air conditioning, heaters, insulation materials, layered clothing, all have the same goal, to minimize the temperature fluctuations the body has to face. And what is the result? Your body no longer receives thermal signals strong enough to activate the systems we have discussed. Your thermoreceptors still work, but they are rarely challenged. Your hypothalamus still regulates temperature, but within a very narrow range. The sympathetic nervous system and the endocrine system no longer have to respond to large changes. And over time, this creates a state that in physiology is sometimes called thermal monotony. Compare this to your ancestors. They had no concept of a comfort zone. They woke up in the cold, worked in the heat, and slept under sharply dropping nighttime temperatures. Their bodies constantly receive signals, constantly adjusted, constantly adapted. Variability was not the exception, it was the default. And because of that, their thermoregulatory, hormonal, metabolic, and immune systems were trained every day. Meanwhile, you live in an environment where those signals have almost disappeared. And here is the key point. When the system does not receive input, it has no reason to maintain high levels of activity. Biology does not waste energy. If a mechanism is not needed in the current environment, the body will reduce its activity. This has been observed in many studies on physiological adaptation, from muscles and the cardiovascular system to the immune system. No stimulus, no adaptation, no challenge, no maintenance. And therefore what you are seeing is not the body getting worse, but the body responding exactly to the environment you have placed it in. The modern environment, with all its conveniences, has removed a very important type of biological input, temperature variability. And when that input disappears, the systems related to it also reduce their activity. This is not a design flaw. It is a logical consequence. And when you look at it this way, you begin to see more clearly what was suggested earlier. The problem is not that your body is broken. The system is still there. It is still operating according to its own principles. It is simply no longer being used. Looking at the entire picture, you begin to realize that the problem does not lie in your body getting weaker. It is not broken. It is not declining in the way you used to think. It is doing exactly what biology forces it to do, adapting to the environment you have placed it in. In physiology, there's a very simple but extremely powerful principle, often summarized by the phrase, use it or lose it. If you use a system, it is strengthened. If you do not use it, its activity decreases. This is not a conscious choice. It is a law. Studies in the field of disuse physiology have shown this repeatedly across many different systems in the body. When you lie motionless for a few weeks, muscle mass can decrease significantly in just 10 to 14 days. Bone density decreases when there is no mechanical loading. The cardiovascular system declines when there is no physical activity. And the same thing happens with less obvious systems, such as thermoregulation or the stress response. When your body no longer has to face cold, it has no reason to maintain the mechanisms for handling cold at a high level. Brown fat, which costs energy to maintain and operate, will reduce its activity if it is not activated regularly. The vasoconstriction response becomes less sensitive. The hormone system related to acute stress is no longer trained the way it once was. This is not weakening in a negative sense. It is optimization. Your body is saving energy by not investing in functions that the current environment does not require. And if you think about it honestly, you will see that it makes perfect sense. Why would the body maintain an energy-consuming system if it is never used? But it is right here that a major misunderstanding begins to appear. You feel less tolerant of cold, more easily shocked, less adaptable, and you conclude that your body has become weaker. But the reality is the opposite. Your body is functioning exactly according to its principles. It is simply adapting to an overly stable environment. And that environment, no matter how comfortable, is not suited to the way your system was designed. This is something many people overlook. Adaptation does not always mean improvement. You can adapt in a way that fits the current environment but moves away from the state where your system functions optimally. Just like a muscle that is not used will atrophy, not because it is broken, but because it is no longer needed under current conditions. Your thermoregulatory system is the same. It does not disappear. It simply reduces to a sufficient level. And when you suddenly place yourself in a cold environment, you are not facing an abnormal challenge. You are encountering a type of signal that your body was once familiar with, but has not been exposed to for a long time. That is why your response is strong, sometimes overly strong. Not because cold is more dangerous, but because your system has not been used. And this is where cold exposure changes its role. It is no longer a challenge to overcome. It becomes a signal for restoration. When you expose yourself to cold in a controlled way, you are reintroducing an input that your system has been missing. You are reminding the body that these mechanisms are still needed. And over time, the body will respond exactly as it always does. It will adapt. But this time, in the opposite direction. Brown fat becomes active again. The vasoconstriction response becomes more efficient. The hormone system becomes more flexible, not because you force it, but because you are re-providing the conditions it was designed to respond to. And when you see this clearly, you will realize that the key statement is no longer a slogan, but an accurate description of biological reality. Your body is not getting weaker. It is adapting perfectly to an unsuitable environment. To understand this, you need to look at the autonomic nervous system, the system that controls nearly every automatic function in your body, from heart rate and breathing to digestion. This system has two main branches, the sympathetic, often called fight or flight, and the parasympathetic, often called rest and digest. But this naming oversimplifies things. In reality, these two systems are not absolute opposites, but two parts of a continuously adjusting system. When you step into cold water, as you have seen, the sympathetic system is strongly activated. Heart rate increases, breathing quickens, blood vessels constrict, and hormones are released. This is the activation phase. But if you stop here, you will miss the more important part, what happens afterward. When you leave the water, when the cold stimulus decreases, the system begins to shift states. And here, the vagus nerve plays a central role. The vagus nerve is one of the main components of the parasympathetic system. It extends from the brain down to the heart, lungs, and many other internal organs, and it is responsible for regulating the body's recovery state. When the vagus nerve is activated, heart rate decreases, breathing becomes deeper and slower, the digestive system works more efficiently, and the body shifts into a state you could describe as calm but alert. What is important is that cold exposure does not only activate the sympathetic system, but also indirectly activates the vagus nerve through this state-shifting process. This is not theory. It has been measured. One of the commonly used indicators is heart rate variability, HRV. HRV reflects the degree of balance and flexibility between the sympathetic and parasympathetic branches. Studies show that people who regularly expose themselves to cold tend to have higher HRV, meaning their autonomic nervous system has a greater ability to switch flexibly between activation and recovery states. This is a sign of a healthy system, not because it is always in a relaxed state, but because it can move between states efficiently. And this is the point where many people misunderstand. They think the goal is to avoid stress, to avoid activating the sympathetic system. But biology does not work that way. You need both. You need the ability to activate when necessary, and no less importantly, you need the ability to return to a balanced state afterward. Cold exposure provides both phases in a short cycle, strong activation followed by deep recovery. And it is this transition that truly trains your system. It is like not only training a muscle by contracting it, but also by releasing it properly. If you only activate without recovery, the system becomes overloaded. If you only stay in a stable state without ever being challenged, the system becomes less flexible. But when you introduce a stimulus like cold, you are creating a controlled oscillation between these two states. You are teaching your nervous system how to turn on and how to turn down. And over time, this improves the overall regulatory capacity of the autonomic system. You not only respond better to cold, but to many other types of stress as well. And that is why the effects of cold exposure do not stop at temperature. They extend to mood, energy, focus, and even the way you respond to pressure in daily life. But all of that comes back to a very simple principle. The issue is not whether you can activate the system. Most people can do that. The issue is how quickly and efficiently you can return to a balanced state. And cold exposure, when used correctly, does not only activate the system, but also trains precisely that ability to return. If you pay close attention to what happens after you leave the cold water, you will begin to recognize a very specific state that is hard to mistake for any other experience. Your heart rate, which had increased sharply, begins to decrease. Breathing becomes deeper and slower. The body is no longer in the tense state it was in at first, but you also do not fall into a sluggish state. Instead, there is a very clear feeling, calm but alert. In physiology, this state has a specific name: parasympathetic rebound. This is the phenomenon where, after an acute stress stimulus, the parasympathetic nervous system not only returns to baseline, but actually operates stronger than normal for a short period, creating a phase of deep recovery. This has been observed in many studies on neurophysiology, especially in experiments involving cold exposure and exercise physiology. When the body experiences a strong but short-term stress, such as cold water or high-intensity exercise, the sympathetic system is activated to handle the situation. But as soon as the stimulus ends, the parasympathetic system, with the vagus nerve playing a central role, turns on to bring the body back to balance. And in the process, it often overshoots the normal level, creating a deeper recovery state than before the stress occurred. This is why you can clearly feel the change just a few minutes after getting out of cold water. It is not like the usual feeling of relaxation when you rest in a chair. It has a different quality. You are not sleepy. You do not lose energy. You are alert, but not tense. This is an important distinction. Passive relaxation usually comes with an overall reduction in stimulation, sometimes leading to reduced alertness. But parasympathetic rebound does not reduce alertness. It keeps the nervous system activation at an optimal level while removing excess tension. Some studies measuring HRV and neural activity after cold exposure have shown a significant increase in indicators related to parasympathetic activity, especially within 10 to 30 minutes after the end of cold exposure. This shows that the body does not just return to normal, but actually enters a better regulated state. You can compare this to the feeling after completing a high-intensity workout. During the workout, you are tense, heart rate high, hormones elevated. But afterward, when you stop, there is a period when the body feels very balanced and clear. Cold exposure creates a similar effect, but through a different pathway, temperature instead of movement. And this leads to a common misunderstanding that needs to be clarified. Many people think the benefits of cold exposure come from the feeling of enduring while in the cold water. But in reality, the most important part may happen afterward, in the recovery phase. That is when your nervous system is reset. Not by willpower, not by thinking, but by its own biological mechanisms. You do not need to try to relax. The system does it itself if you provide the right type of stimulus beforehand. And when you repeat this process many times, what happens is not only that you tolerate cold better, your nervous system learns to switch between states more efficiently. It becomes more flexible. It does not get stuck in a prolonged activation state like when you have chronic stress. It also does not become sluggish due to lack of stimulation. It begins to operate the way it was designed, oscillating, adjusting, balancing. And that is the key point of this entire section. You are not only activating the system when you step into cold water, you are teaching it how to return. You are training resilience, not just endurance. And in a world where most stress is chronic, prolonged, and without a clear endpoint, that ability may be more important than anything else. And if you go one layer deeper, below the level of hormones, below even the nervous system, you will reach a place that most people never think about when they step into cold water. The individual cells in your body, and more specifically the small structures inside them called mitochondria. This is where most of your energy is produced. Each cell can contain hundreds to thousands of mitochondria, and they function like microscopic power plants converting nutrients into ATP, the form of energy the body can use. But what matters is not only how much energy you have, but how efficiently you produce and use it. And this is where cold exposure begins to create a change that you cannot feel directly, but can be measured. When the body is exposed to cold, especially cold strong enough to activate thermogenesis, the demand for heat production increases. One of the ways the body responds is through brown fat, which has a very high density of mitochondria. But these mitochondria operate differently from normal mitochondria. Instead of optimizing for ATP production, they can uncouple the process to produce heat through a protein called UCP1. This allows energy from nutrients to be released as heat instead of being stored. And to do that, the body needs more mitochondria and needs them to function more efficiently. Studies in cell biology and metabolism, including those published in journals like Cell Metabolism over the past decade, have shown that repeated cold exposure can increase mitochondrial density, a process called mitochondrial biogenesis. This does not only happen in brown fat, but can also affect other tissues such as skeletal muscle. At the same time, the performance of mitochondria is also improved, meaning that with the same amount of nutrients, the body can produce energy more efficiently or more flexibly in switching between different forms of energy. This is a very important point. Many people think about energy in a simple way. You burn calories to create energy. But the body is not only concerned with the amount of energy, it is concerned with how that energy is used. An efficient metabolic system does not only produce more ATP, but also has the ability to adjust between storing, using, and releasing energy as heat when needed. Cold exposure promotes exactly that flexibility. It forces the body to shift from an energy-saving state to an energy-consuming and regulating state. And over time, this changes the way the system operates at the cellular level. This is not something you can feel immediately. You do not feel your mitochondria working better, but you can see its consequences: more stable energy levels, better endurance, more effective stress responses, and all of that begins with very small changes at a level the naked eye cannot see. This also clarifies another misunderstanding. Cold exposure is not just about burning more calories to lose weight. If that were all, it would be a very limited tool. But in reality, it is changing the way your body handles energy from the root. It does not only increase output, it optimizes the entire system of energy production and use. And when you look at it this way, you begin to see that what is happening is not a surface effect. It is a restructuring at the cellular level. Each time you expose yourself to cold, you are sending a signal down to the smallest units of your body, forcing them to adapt, to become more efficient, to become more flexible. And over time, those small changes accumulate. Not in the form of a temporary sensation, but in the form of a system that operates differently. Cold exposure, in that sense, does not only affect how you feel, it is rewriting the way your cells function. Looking at everything we have just covered, from the nervous system, hormones, and metabolism, down to the mitochondria in each cell, you will begin to see a common principle, repeating at every level. And that principle has a very specific name in biology: hormesis. Hormesis is the phenomenon in which a small amount of stress, when applied correctly, can create large benefits for the system. It sounds counterintuitive because you usually think of stress as something to avoid. But in biology, the issue is not whether there is stress or not, but the type of stress, its intensity, and its duration. A small dose for a short time can activate adaptive mechanisms that make the system stronger. A large or prolonged dose, on the other hand, causes harm. You have seen this principle before. You may just not have named it. Exercise is a form of hormesis. When you train, you create mechanical stress on the muscles. Muscle fibers suffer minor damage, and the body responds by repairing and rebuilding them stronger. Short-term fasting is also a form of hormesis. When there is no continuous energy supply, the body activates recycling and energy optimization mechanisms. Temperature works the same way. Both heat and cold can serve as hormetic signals if applied correctly. And cold exposure is one of the clearest forms of hormetic stress. It is strong enough to activate the system, but if controlled, not strong enough to cause damage. Studies in biology and medicine over many decades have shown that stimuli of this type can lead to adaptive changes at many levels, from gene expression and enzyme activity to cell structure. But what matters is not a single exposure. If you only step into cold water once, you will have a strong response, possibly very impressive. But most of those changes are temporary. What is truly important is what happens when you repeat that signal. The first time, your body reacts strongly because it is not used to it. The nervous system activates maximally, hormones spike, and the shock sensation is very clear. But if you repeat it day after day, week after week, that response begins to change. Not because the stimulus weakens, but because your system has learned to handle it more efficiently. Heart rate does not rise as high as before. Breathing stabilizes faster. The discomfort decreases. At the same time, deeper changes such as brown fat activity, mitochondrial performance, and nervous system balance begin to be maintained at a higher level, even when you are not in cold water. This is adaptation. And it does not happen because you try hard or have strong willpower. It happens because your biological system is designed to learn from repeated signals. You do not need to convince the body to change. You only need to provide a clear enough, consistent enough input and let the system do the rest. This is the point that many people miss when they approach cold exposure as a test of willpower. They focus on enduring as long as possible, as cold as possible. But biology does not care how much you endure. It cares whether you provide the signal consistently. A moderate stimulus, repeated regularly, is often far more effective than an extreme but rare one. And when you look at the entire process, you begin to see something very different from the initial way of thinking. You do not become stronger just because you tolerated the cold. You do not accumulate strength in a linear way. Instead, you are readjusting the way your system responds to a specific type of signal. You are teaching the body to handle stress more efficiently, to switch between states faster, to use energy better. And all of that comes from a very simple but profound principle. You do not become stronger because of the cold. You become more adapted because you repeat the signal. At this point, there is something that needs to be stated very clearly before you continue. This biological system is not infinite, and cold exposure is not a game of pushing limits to the extreme. Biology always operates within an optimal range, and once you go beyond that range, the mechanisms that help you adapt can quickly become mechanisms that cause harm. Cold water can be a useful signal, but at a certain level, it shifts from a stimulus to a danger. When water temperature drops below around 5 degrees Celsius, especially if you're exposed for a prolonged time, the body begins to lose heat faster than its ability to generate it. This is no longer homeostasis. This is an energy imbalance. And when that happens, the system no longer adapts. It begins to lose function. Hypothermia is a very clear example. When core body temperature drops below 35 degrees Celsius, enzymes in the body begin to function less efficiently. Below 33 degrees Celsius, neurological function is noticeably affected. You may lose motor coordination, experience cognitive decline, and even fail to recognize that you're in danger. Below 30 degrees Celsius, the risk of serious cardiac arrhythmias increases significantly. And below 28 degrees Celsius, the risk of death becomes very high if timely intervention is not provided. These are not theoretical numbers. They have been documented in numerous studies on underwater physiology and emergency medicine. Research by physiologists such as Michael Tipton at the University of Portsmouth has shown that heat loss in cold water occurs much faster than in air, because water conducts heat about 25 times better. That means you can enter a dangerous state faster than you think, even when you feel like you can handle it. This is the important point. Your sensation is not a reliable indicator of your actual physiological state. When the nervous system is affected, your ability to assess risk decreases. And that is why cold exposure must be approached as a controlled process, not as a challenge to prove yourself. You do not need to stay in cold water longer, colder or more extremely to gain the benefits. As you saw in the previous section, your system responds to the signal, not to the extreme. A sufficient stimulus repeated regularly creates adaptation. An excessive stimulus that exceeds the body's regulatory capacity only creates uncontrolled stress and can lead to damage. Biology does not reward recklessness. It rewards consistency and staying within the system's limits. This also aligns with the principle of hormesis you just saw. Hormesis only works within a certain window. Below that level, the stimulus is not strong enough to create change. Above that level, the stimulus becomes harmful. And cold exposure falls under the same principle. It is not a straight line where more is better. It is a curve, where there is an optimal zone that you need to find and maintain. This requires you to observe your body, understand its responses, and adjust the level of exposure appropriately. Not by willpower, but by awareness. You do not need to prove that you are strong by enduring longer than others. That is not the goal of this system. The goal is activation, adaptation, and recovery. And to achieve that, you must respect the limits that biology sets. When you understand this, the way you view cold exposure changes completely. It is no longer a challenge to overcome, but a tool to use, a powerful tool. But like any powerful tool, it needs to be used correctly. You do not hit harder to get better results. You adjust the force to match the material. Your body is the same. It does not need extremes. It needs the right signal. And that signal must stay within the limits the system can handle. If not, you are no longer helping the body adapt. You are pushing it into a state where its own protective mechanisms cannot keep up. You may begin to see a very clear boundary between the two things we have been talking about from the beginning, biology and physics. Biology allows you to adapt, adjust, and respond flexibly to the environment. But physics does not negotiate. It does not care whether you are used to it or not, whether you have willpower or not, or how long you have trained. It only follows its laws. And when you talk about cold exposure, you are standing exactly at the intersection of those two systems. Your body can increase heat production, constrict blood vessels, activate hormones, and optimize metabolism. But at the same time, heat is still leaving your body according to very specific laws of thermodynamics. Heat always moves from a place with higher temperature to a place with lower temperature. There are no exceptions, and the speed of that movement depends on the environment around you. Water conducts heat about 25 times better than air, a fact that has been measured in basic physics studies since the 20th century and is widely applied in environmental physiology. That means when you are in cold water, your body loses heat about 20 to 25 times faster than when you stand in air at the same temperature. This is why 15 degrees Celsius in water feels much more severe than 15 degrees Celsius in air. And this is also why the biological responses we have discussed must be activated so quickly and strongly, because if not, you would lose heat too fast. But there is a very important point that needs to be clearly understood here. Biology can delay the heat loss process. It can slow it down, optimize it, redistribute resources. But it cannot break the laws of physics. It cannot generate infinite heat. It cannot retain heat forever in an environment where heat is continuously being pulled away. And therefore, every adaptive process exists within limits set by physics. You can increase the activity of brown fat to generate heat. You can constrict blood vessels to preserve heat for vital organs. You can increase metabolism to create more energy. But all of that consumes energy and has limits. When the rate of heat loss exceeds the ability to generate heat, the system will begin to fail. Not because you are not strong enough, but because you have crossed the physical limit that the body can compensate for. This is why cold exposure must always be controlled, not because it is dangerous by default, but because it directly involves physical processes that you cannot change. You can train the nervous system, you can improve metabolism, you can increase endurance, but you cannot change the thermal conductivity of water. You cannot change the direction of heat movement. You cannot change the fact that heat will continue to leave your body until it reaches equilibrium with the surrounding environment. This also explains why people with experience in cold exposure usually do not try to extend the time indefinitely. They understand that the benefits come from activating the system, not from defeating physics. A short period that is sufficient to trigger the response is enough. After that, staying longer no longer provides significant additional benefits and only increases risk as the body begins to lose heat beyond its ability to compensate. This is not a competition between you and the cold. It is an interaction between your body and the physical environment. And in that interaction, physics is always the unchanging foundation. Biology can only operate within the limits that physics sets. When you understand this, you begin to look at cold exposure with a different kind of respect. Not fear, but a clear awareness of the boundaries. You know which systems you are activating. You know where the limits are, and you do not try to cross them just to prove something. Because in the end, if you go too far, if you stay too long, if you let the rate of heat loss exceed the ability to generate heat, then the outcome no longer depends on your level of adaptation. It depends on the laws of physics that existed long before biology. And in that case, physics always wins. Going back to the starting point, a very simple action you have performed many times without thinking much about it, stepping into cold water. You feel cold, your body flinches. You endure for a few seconds or a few minutes. Then you step out and think the experience is over. But if you look back at everything we have just covered, you will see that that sensation is only the surface. The moment the water touches your skin, a chain of responses has already begun. Your nervous system activates in milliseconds. The hypothalamus sends signals. Hormones are released. Noradrenaline rises by hundreds of percent. Dopamine changes. Blood vessels constrict. Heart rate increases. And all of that happens before you even have time to think about it. But what is more important is what happens afterward. When you step out of the water, when the cold sensation decreases, the system does not shut off. It shifts states. Parasympathetic rebound begins. The vagus nerve becomes more active. Heart rate drops below the previous level. The nervous system becomes more stable. The changes in hormones do not disappear immediately. Dopamine remains elevated for many hours. Noradrenaline decreases gradually but leaves behind a prolonged state of alertness. At a deeper level, brown fat has been activated, mitochondria have been awakened, and metabolism has changed the way it uses energy. The immune system is not left out either. Studies show that changes in cytokines and immune cell activity can last for hours, even days, after a single cold exposure. All of this happens without you feeling it directly. You do not feel hormones moving in your blood. You do not feel mitochondria increasing efficiency. You do not feel the immune system adjusting. You only feel cold, then no longer cold. But in reality, the system is still working. And this is the point where your perception diverges from biological reality. You judge the experience based on sensation, while most of what is important happens outside that range of sensation. A small action lasting a few minutes has triggered a chain of responses that last for hours. A simple thermal signal has traveled through the nervous system, the endocrine system, the metabolic system, the immune system, and loop back to influence your psychological state. This is not a localized effect. This is a whole system response, and when you look at it that way, you begin to see the very clear mismatch between cause and effect. Very small input, very large output. You do not need a complex intervention, a chemical compound, or advanced technology. You only need the right physical signal in the right place, and your system will do the rest. This also explains why the changes you feel often do not occur immediately while you are in the cold water, but appear afterward. The clarity, the focus, the feeling of stability all come from the recovery phase, from the way the system rebalances after being activated. And when you repeat this action day after day, those changes are no longer just temporary. They begin to accumulate. Your system learns to respond faster, recover better, and use energy more efficiently. Not because you force it, but because you provide the signal consistently. And this is the most important thing you need to take away from this entire story. You step into cold water and think it is just a sensation. But in reality, you have activated a system. And that system does not stop when you step out. I'm not telling you that you must do this. There is no command here. There is no mandatory formula you have to follow. Because this whole story is not about convincing you to change your behavior, but about you clearly understanding what is really happening beneath those very simple actions you have become so used to that you no longer question them. You have seen that even a short exposure to cold water can activate the nervous system, change hormones, adjust metabolism, affect the immune system, and even reach down to the cellular level. You have seen that those changes do not stop when you step out of the water, but continue for many hours, sometimes longer, and all of that happens without willpower, without belief, without any effort in the psychological sense. It is simply the way your system responds to a type of signal it was familiar with for most of its evolutionary history. And now you have also seen something else, perhaps even more important. The environment you are living in has almost completely eliminated that type of signal. The temperature around you is kept stable almost all the time. You rarely have to face sudden changes. You rarely have to let your body regulate itself the way it was designed to. You have built a world where variability is considered inconvenient and needs to be eliminated, where everything is optimized for continuous comfort. And that is not wrong. It is an achievement of technology and civilization. But it also creates a consequence that you often do not see. Your body no longer receives a type of input it once depended on. And when a system does not receive input, it adapts by reducing its activity, not because it is broken, but because it is doing exactly what biology requires. And then you look at your current state, feeling low energy, lacking flexibility, easily affected by prolonged stress, and you begin looking for solutions outside. While part of the answer may lie in the fact that you have removed those very basic signals from your environment, and that is where the real question arises. It is not whether cold exposure works or not, because you have already seen that it activates very clear and measurable mechanisms. The question is, why you removed it from your life in the first place? Why are you living in an environment where your body almost never has to do what it was designed to do? Why do you treat absolute stability as the default when your system was built to handle change? And I'm not giving you a definitive answer because this is not a problem with a single solution. You can choose to continue living in the current environment and change nothing, or you can begin to reintroduce some of the signals you have lost in a way that fits you within your limits. With the understanding you have just gained, what matters is not whether you do it or not, but that you clearly understand the consequences of each choice. You no longer see small actions like taking a cold shower or avoiding cold as random habits. You see them as signals, as inputs that your system responds to in very specific ways. And when you have that perspective, you begin to see everything else differently. Not just cold, but the way you interact with the environment in general, the way you understand your body, the way you question what you consider normal. And perhaps that is the most important thing I want to leave with you. Not advice, but a question you can carry with you. You are living in an environment your body was not designed for, and you have removed a signal it once depended on. So do you really understand what that means, or are you just continuing to live in that stability without ever stopping to ask why? If you want to understand more deeply what your body is really doing every day, subscribe to the channel so you don't miss the next analyses. Thank you for following along, and I will see you in the next question that you may not have thought about before.